Okay, welcome back. So now what we're going to do is we're going to start doing hypothesis testing, and we're going to start using the 7-step process. And what we're going to do is we're going to start with testing claims about the mean, the population mean. And so we're going to start assuming when we have that we know sigma. And so in that case, we're going to use the z distribution, and we're going to use eventually what we're going to talk about is the z-test on your calculator. So we're going to use the traditional method, the p-value method, and then I'll show you the z-test on your calculator that will give you both your test statistic if you want to do the traditional method, or the and it'll give you the p-value so you can do the p-value method. And then what we're going to do is we're going to then say, hey, what if we don't know sigma? And then, just like in confidence intervals in Chapter 8, we're going to use the decision making that if we don't know sigma, the population standard deviation, then we're going to use the t-distribution again. So in this case, we're going to use a t-test. Okay? So when it comes to testing claims about the mean, it's going to ultimately come down to either a z-test or a t-test, and which test we use is going to be determined by whether sigma is unknown or known. So that's where we're going to go. So let's start with an example. So the example I want to use is this one. So it says here that a machine at a bottling plant is programmed to fill bottles to an average volume of 12.2 ounces. The volumes are normally distributed with a standard deviation of sigma equal to 0.6 ounces. The line manager suspects that the machine may be overfilling the bottles, and so he will test the claim that the mean is greater than 12.2 ounces. A sample of 36 bottles is selected. The sample mean is 12.5 ounces, and the p-value is calculated to be p is equal to 0.00313. What can you conclude from this test? Okay, well, let's do this a little bit differently. I'm going to do the 7 steps. Even though they give you more information than you need, let's go through and let's just say we've got the sample data and we've got the claim. So let's start with the claim. It says a machine at a bottling plant is programmed to fill bottles to an average volume of 12.2 ounces. Okay, that's what it's programmed to. So overall, the average volume should be 12.2 ounces. Okay, the volumes are normally distributed. Excuse me. So here we have X. So this is the volumes of, let's see, the volumes of liquid. So we know the volumes of liquid are normally distributed, and with a mean of 12.2 ounces, that's what they just said, that's what it's calibrated. The machine is calibrated for 12.2 ounces. And the standard deviation, sigma, is equal to 0.6 ounces. Okay, so that's what we know. And just make sure, oh, I'm a little too low, too high. Yeah, let me do this. So X is normally distributed with a mean of 12.2 ounces and a standard deviation equal to 0.6 ounces. Okay, so now that is the volumes of liquid. Now the line manager suspects that the machine may be overfilling the bottles. Well, what does that mean? So he's claiming, so he suspects and claims that the machine is overfilling the bottles. Okay, so what does that mean? It means that on average, it's putting more than what the machine is calibrated to put in, which is 12.2 ounces. So he's claiming that overfilling the bottles means that it's putting in more than 12.2 ounces of liquid in each bottle on average. So that means that mu is actually greater than 12.2 ounces. That's the claim. So now, step one. So here's step one. Step one is setting up your hypotheses. So step one here is going to be the null and the alternative hypotheses. So the alternative is this because it's greater than. There's no equal sign. So this is going to be mu is greater than 12.2 ounces. And so that means what's the null? The null is going to be the opposite, the contradictory statement. So it's going to be mu is less than or equal to 12.2 ounces. Okay? So now, that's step one. What's the claim? Here. So we want to make sure we note the claim. Also, what's the test? It is going to be a right tail test. Okay? Now, we're finished with step one. Now, step two is always going to be the same no matter what the hypothesis test is. Step two is always we're going to assume the null is true. So we always assume the null is true. In other words, we're going to assume for this problem that mu has not changed, that the average amount of juice or fluid in each of these bottles has not gone up. So it has not changed. So it's still equal to 12.2 ounces. So that's what we're going to assume. Okay? So now, step three is we're going to write down all the information that they give us in the problem and determine the distribution of the sample statistic. In this case, the sample statistic is going to be x bar. We need to know that the distribution of x bar is what? Normal. Okay? So, before we can do the test, we need to know the distribution of x bar. The sampling distribution is normal. So now, what do they tell us? We want to write down the first thing is the significance level. So the significance level that they want us to test is, let me see here, 0.05. So alpha is equal to 0.05. Also, if the problem doesn't specify an alpha level or a level of significance, we always assume alpha is equal to 0.05. Okay? So alpha here is 0.05. The sample size was 36, right? They took 36 bottles. And they found that the average volume for these 36 bottles was 12.5. 12.5 ounces. Okay, now, here's the question. Oh, by the way, we know sigma. So sigma is equal to 0.6 ounces. Okay, so we know that. So this is all the information they give us. Oh, and we also know that x is normally distributed, right, with a mean equal to 12.2 and a standard deviation of equal to 0.6 ounces. Okay, now, what we need to know is the distribution of x bar, right? We want the distribution of x bar to be normal. Okay, so is it normal? Well, yes. Why? Because we actually get it two ways. Since the population is normal, remember from chapter 7, if the population is normal, the sampling distribution will always be normal for x bar. Also, look at the sample size. The sample size is bigger than 30. So the central limit theorem also gives it to us. So we have it both ways. So now, what is the distribution? It's going to be normal with a mean that's equal to the same. So it's going to be mu, which is under the null, is 12.2 ounces, right? We're assuming the null is true. So that's the mean we're going to use. The standard deviation for x bar is sigma divided by the square root of n, which in this case is going to be 0.6 divided by the square root of 36. Okay, now that's the information we're going to use in step 4. So here's the key. We need to know this, because that means that we're going to be able to do the test. Okay? So now, if we go to step 4, right? So step 4 is right here. Okay, so if we go to step 4, now we can go do either the traditional method or the p-value method. So let's do the traditional method first. Now, I want you to leave room on your paper for both the traditional method and the p-value method, because I'm going to erase this. And so for step 4 and 5, or step 4 rather, and step 5, I want you to leave a little bit of room for each, because we're going to go back. So I want you to make sure you leave room to put your work in. Okay. Now, also keep in mind that these are 2 separate methods. You pick one and you do it. Don't do both methods for the same problem. Okay. I'm just doing it for illustration purposes, okay? So, on an exam situation for the homework, you use whichever method you want to use, okay? Unless it specifically tells you, or I specifically tell you on the exam to use the traditional method or the p-value method. Otherwise, if I don't say anything, use whatever you want to use, okay? So I'm going to show the traditional method first. So the traditional method in this case, the first thing, I'm going to calculate our test statistic, z star. So again, I'm going to use the z-score formula. So it's going to be x bar minus mu naught divided by sigma over the square root of n. And so if I just plug in the values from 3, this is where 3 comes in, right? So x bar is 12.2, or excuse me, 12.5. Mu 0 is assumed to be 12.2. Divided by sigma, which is divided by the square root of n, which is this right here, 0.6, divided by the square root of 36. And so if I calculate that out, what do you get? Well, let's find out. So 12.5 minus 12.2, and then we're going to divide by hold on a second here. Okay, so and so we end up with 3. Okay, so in this case, our test statistic turns out to be 3, exactly 3. So 3 standard deviations above the mean. Okay. So right now, I'm already thinking we're probably going to end up rejecting this just because of what I know about the empirical rule, right? So remember, 3 standard deviations above the mean. But anyway, let's just figure it out. So now, if I'm using the traditional method, I also need my z alpha, right? My critical value. Well, how am I going to get that? That's where my calculator comes in, or the z table. So what if I know, again, normal distribution? That's what gives it to me. Is I know that it's a normal distribution. Since it's a normal distribution, I can use inverse norm. And to find my critical value, I have to know the area to the left of my critical value. Well, again, if you don't know it, draw out the curve. So I know here, if the area to the left, right? Or excuse me, the area to the right. So the area to the right, it's a right-tailed test. So the area to the right has to be equal to alpha. Alpha is 0.05, so I know that this area has to be 0.05. So the area to the left of my critical value is 1 minus that, or 0.95. So I'm going to put 0.95 here, followed by 0, 1, because it's a standard normal. And what does my z-score turn out to be? Well, it's going to turn out to be 1.645. Okay? And so now, this is step 4. Step 4 is doing my test. Step 5 is now doing the comparison. So now what I'm going to do is I'm going to run my comparison using the traditional method. So now, it's a right-tailed test, which means I'm going, again, with the traditional method, I'm going to reject the null hypothesis if what? If my test statistic is inside the rejection region. So in other words, I'm going to reject for a right-tailed test if my test statistic is greater than or equal to my critical value. So in this case here, z star, which is equal to 3, z alpha is 1.645, is my test statistic bigger than my critical value? And the answer is yes. Okay? So therefore, step 6, now, it falls within the rejection region. So that means I'm going to reject the null hypothesis. So again, my 3 dots, my triangle of dots is therefore, so the conclusion, so, or the result. So therefore, what? We reject the null hypothesis. Okay? So that's the first 6 steps. The final step is the conclusion. Now, this is where we have to go back to the claim and we have to tell our audience in non-technical terms what happened. Okay? Is there evidence to support the claim? Is there not enough evidence to support the claim? Is there enough evidence to reject the claim? Is there not enough evidence to reject the claim? It's going to be one of those 4 conclusions. Okay, and I'm going to tell you exactly how I would phrase it. Okay? Now, the first thing to notice is the claim is the alternative hypothesis. If the claim is the alternative hypothesis, your two conclusions will be either one of these two. So if the claim is the alternative hypothesis, you're either going to have one of these 2 conclusions, nothing else. Either there is going to be strong evidence or significant evidence or sufficient evidence to support the claim, or the other conclusion is that there is not enough evidence to support the claim. Okay, or there is no significant evidence to support the claim. Those are the only 2 options if the claim is the alternative hypothesis. Okay, so in this case here, we reject the null. So what does that mean? It means that we reject this. So that means that there is enough evidence to support the alternative hypothesis. So if we reject the null hypothesis, that means that there is strong evidence to support the alternative hypothesis. And since the alternative hypothesis is the claim, we would say that there is strong evidence to support the claim. That's it. Now the way we phrase this goes back to what the claim is. Right? The claim is that the machine is overfilling the bottles. So is there enough evidence to support that claim? The answer is yes. At an alpha level. So here's the key. We have to mention the alpha level. This is good only at a specific alpha level. So the way we would state this is at an alpha level or a significance level, or you could say alpha equal to. So there's different ways you can phrase it. But at an alpha level equal to 0.05, there is strong evidence, okay, based on the sample data, okay, to support Whose claim? It's the line manager's claim, right? But you don't have to say that, but you could just say, to support the claim, the machine is overfilling the bottles. That's it. So make sure you get this idea of how to write the conclusion. Because we want to write the conclusion in layman's terms, in non-technical terms, right? We don't want to talk about null hypotheses, rejecting p-values, all of this stuff. All we want to do is go back to the claim and say, hey, in this case, is there enough evidence to support the claim or not enough evidence to support the claim? So in this case, add an alpha level, because again, it's based on the significance level and the sample data. Okay, so if we used a different alpha level, right, we might have gotten a different result. Or if we used a different sample, we might have got a different result. We don't know. But based on the sample and the significance level, this is the result. Okay, so add an alpha level of 0.05 or 5% if you want to say it that way. There is strong evidence based on the sample data to support the claim that the machine is overfilling the bottles. And that's it. And that's how you do the 7 steps using the traditional method. Okay. Now what I'm going to do is I'm going to erase 2 of the steps. So what I'm going to do is I'm going to erase this. So 4 and 5 I'm going to leave blank. So now what I'm going to do is I'm going to do the p-value method here, and notice how everything else stays the same. Okay? 6 is going to be the same, and 7 is going to be the same, because remember what I said, it's the same test. Okay? So now, here's how we're going to do the p-value method. So what I'm going to do is I'm going to calculate the p-value, right? So p-value in this case, since it's a right-tailed test, is the probability that my test statistic, x bar, my sample mean, is bigger than or equal to what? Well, bigger than or equal to what I got, which is 12.5. So now, since I know that the distribution of x bar is normal, I can just use normal CDF, right? So normal CDF is going to give me the p-value, the probability, right? So what's the lower bound here? Well, the lower bound here is 12.5, okay? The upper bound, I'm just going to use 10 to the 99th power. And then the mean, what's the mean? The mean is the mean of the distribution, which is 12.2 under the null, right? 12.2. And then the standard deviation is what? It's the standard deviation from the distribution, which is 0.6 divided by the square root of 36. And I would just put it right into your calculator this way. Don't calculate this separately and then stick it in here. You could just stick 0.6 divided by the square root of 36 right into your calculator and you'll be fine. Okay? So now, what do you get when you stick that in your calculator? Well, let's find out. Okay, now again, I'm using the computer, but you can use your calculator to get the same answer. Okay, so let's do this. So mu is 12.2, and the standard deviation is what? Hold on a second. Point 1. And we want the probability, it's a right-tailed test, so we want the probability being greater than what? 12.5. And we get 0.0013. So we get 0.0013, and now that's it. We got our p-value, right? So the p-value is 0.0013. So now what do? Step 5 is our comparison. So now, what are we going to compare? We're going to compare p-value to what? Alpha. So now, our comparison is going to be this. P-value is equal to what? 0.0013. Alpha is equal to 0.05. And so again, we ask the question, is p-value less than alpha? That's the rule for the p-value method. Is p-value less than alpha? And the answer is, of course, yes. And again, if p-value is less than alpha, then the result is the same. We reject the null hypothesis, and then our conclusion stays the same. So again, so there's the p-value method and the traditional method. Okay? So now, let's show you how to do the calculator. Now, here's where I'm going to introduce the calculator. So now, there is a function on your calculator that will give you both the p-value and your z-star value. Okay? So it'll give you both of the things you need in order to do either one of the tests, either the traditional method or the p-value method. Okay? Now, the test that you're going to use is the z-test. Why are we going to use the z-test? Because we're dealing with a mean, right? It's a claim about the mean, the population mean, and sigma is known. Okay? So in this case, we're going to use t-test. Now, with the t-test, it's going to give you two options, right? You're either going to use data or statistics. So just like with the confidence intervals, you're going to either use the data option or the statistics option. In this case here, since we're using statistics, we're going to use stats. And then the only other thing you need to tell it is what, now this is important, you need to make sure you put in the right numbers. The first thing it's going to ask you is for what mu naught is, mu sub 0. Well, what's mu sub 0? It's going to be this, the 12.2. So you're going to need to put in mu sub 0. You also need to put in sigma. You need to tell the calculator what sigma is. Okay? You also need to tell the calculator what x bar is. Okay? So x bar, you need to put x bar in there. And also n, the sample size. Okay? And the last thing you need to tell the calculator is what is the test? What alternative hypothesis are you testing? So you make sure you got to put in greater than mu naught. It's got to be greater than. So what you're going to put in is greater than mu 0. Okay? And then what you're going to do is you're going to choose calculate. Okay? And then once you hit enter, it's going to give you your z-star and your p-value. And then here, for step 5, you can use either one. Okay? So you can use the p-value method or the traditional method comparison here. So the t-test on your function is an awesome function on your calculator. I would use it all the time. But make sure you understand how to do the traditional method and the p-value method. Okay? Oh, and by the way, you don't ever have to worry about doubling this if it's a two-tailed test, because the p-value, because by telling the calculator which test you're doing, if it's a two-tailed test, if it's not equals here, then it will automatically double it and give you the correct p-value. So you don't have to double this. It is the p-value. Okay? So that's another great thing about the calculator function here. Okay? So that's one problem. So let's do another one. So now, let's do another one. And this time, I'm going to use the calculator to do the function. So to use z-test. Okay, so let's see here. Let's see what we got here. Okay. Let's see here. Okay, so here's what we have. We have the mean throwing distance of a football for Marco. No, let's not do that one because we don't have the. Let's do. Oh, let's do this one. Yeah, this one better. Okay. Excuse me. Oh, need some water. Okay, sorry about that. Okay, so let's do this example here. It says, according to a recent study, the mean cost of a heart bypass operation is slightly less than $26,100, and approximately 230,000 operations are performed annually. Large sample size or large population. It says a sample of 36 bypass operations showed a mean cost of $25,000. Assume the population standard deviation is $2,400. Develop and test an appropriate hypothesis to see whether or not the mean bypass operation is less than $26,100 using an alpha level of 0.05. So let's write down the information. Oh, okay. Just got something stuck in my throat. Okay, so what do we have here? So the first thing it says, according to a recent study, the mean cost of a heart bypass operation is slightly less than $26,100. Okay, so we're right here, they're saying mu is $26,100. Okay, and that's from a population of 230,000 operations performed annually. They take a sample of 36 bypass operations and showed that the average cost of those 36 operations was $25,000. If we assume the population standard deviation is equal to $2,400, so sigma is equal to $2,400, it says develop and test the appropriate hypothesis to see whether or not the mean bypass operation, the mean cost for this bypass operation is less than $26,100. So now, they want to test the claim whether it's below $26,100, right? So below means less than. So the claim is that the average cost for bypass surgeries is actually less than $26,100. So less than this amount. Okay, that's the claim. So step one, our hypotheses, right? So the alternative is going to be this because it's the one with less than. It does not have equals. Remember, the equal sign is always the null. So in this case, it's going to be mu is less than 26,100 for the alternative, and that is our claim, right? And the null has to be then is greater than or equal to $26,100. And now, in this case here, it's going to be a left tail test, okay? So now step two is always the same. We're going to assume the null is true. In other words, we're going to assume that the population mean hasn't changed, that it's still equal to $26,100. And so now going forward under that assumption, we're going to use an alpha level of 0.05 because that's what they give us. We know the population is normally distributed, right? So it's normally distributed with a mean of assumed, right, mu naught. We're assuming the mean is equal to $26,100 with a standard deviation of $2,400. Okay? And also, we know that the sample, right, what did they give us? They give us a sample size of 36 again. Again, just so you're aware of something, I don't know why they keep using these numbers that are really easy, like 36 and things like that. It's not always going to be easy numbers. So it's not always going to be 36. It could be 50, it could be 100, it could be 10, it could be 75. Okay, so just be aware that it's not always going to be nice numbers to deal with. So in this case, n again is 36. And what else? Oh, sigma. What's sigma? Well, sigma is here. So they give us sigma. We know sigma. And now we want to know what is the distribution of x bar. That's the whole purpose of this. Not only writing down the information from the problem, like the significance level and the statistics, but we also need to write down what the distribution of x bar is. Okay? So in this example, in this sample, the average for the 36 turns out to be $25,000. So that's the average. And we need to know the distribution of x bar. So the distribution is what? It's normal. Why? Well, we got it here. The central limit theorem, right? N is bigger than 30, at least 30, but also the population is normal. So we got it both ways, okay? So we know that x bar is going to be normal. And of course, the mean is going to be the same. Mu is equal to mu naught, which is $26,100. And the standard deviation, though, is going to be sigma divided by the square root of n, which is going to be 2,400 divided by the square root of 36. So again, this is what we're using. This is what we're using. Okay? So now, based on this information, let's do our test. So step 4, we're going to use a, what test? Z-test. Oh, sorry. Eat that. So we're going to use a z-test. Apologize for that. So the z-test is going to be based off the fact that we know sigma. Okay, so we're going to use a z-test. And so remember, what we have to put into the calculator for the z-test is we need to tell what mu 0 is. What's mu naught? Mu naught is 26,100. Okay? What is x bar? X bar is 25,000. Okay. What is n? N is 36. What is s, or not s, sigma is 2,400. And we also have to tell the calculator what what is the alternative hypothesis. So in this case, it's going to be less than mu naught. And so what it's going to do is it's going to give us, based on this information we put into it, and again, we're using the stats option here too. Just keep that in mind. We're using statistics. So you have to choose the input option stats for this. Okay? But once we stick this information in, it's going to give us our z star, and it's going to give us our p-value. Okay? And once we have those two, then we can do the traditional method or the p-value method for step 5 in the comparison. Okay? So now, keep that in mind. So now I'm going to do it by hand because I don't have my calculator. So, but again, use the calculator to verify that these are correct. But I'm going to do it by hand so you can see that it still works. So, Z star is going to be what? It's going to be x bar minus mu naught divided by sigma over the square root of n. And so x bar is 25,000 minus mu naught, which is 26,100. Oops. Divided by 2,400 divided by the square root of 36. And so what do we get for our critical value? Let's find out. You get negative 2.75. So you get negative 2.75 for your critical value. And so now, if we want to do the traditional method, then we would have to take our test statistic, negative 2.75, compared to our critical value. And remember, it's a left-tailed test now. So in this case here, we're going to use inverse norm. And we have to find out what the area to the left of this value. So if you draw your little diagram, right, we're over in the left tail. Well, what is the area to the left? What is the area in the tail for a left-tailed test? Remember, it's alpha. Alpha is the area in the tail. So now, what's the area to the left that you're going to put in your calculator? 0.05. Followed by 0, 1, the mean and the standard deviation. And so if you put in 0.05, you're going to get negative 1.645 as your critical value. Now, the comparison. Since it's a left-tailed test, we're going to reject if our test statistic falls within the rejection region. In other words, if it's less than or equal to or less than our critical value. So now, if we set it up, Z star, which is equal to negative 1.645, okay? And our Z alpha, our critical value, is equal to got it the other way around, sorry. Our test statistic Z star is negative 2.75. Our Z alpha is negative 1.645. Is our test statistic less than our critical value? The answer is yes. So it is less than or equal to, therefore, what's the conclusion? We reject the null. So again, if our test statistic falls within the rejection region, we reject the null. And so that's why you draw the picture if you're ever confused. Okay? So that's the traditional method in this problem. Now the next example is the p-value methods, or let's do the p-value method. Okay? So again, what we're going to do is now we're doing a left-tailed test. So p-value, again, so this is a separate method. So this is the p-value method now. Okay? So the p-value method, we're going to calculate p-value. So p-value is equal to the probability of having as extreme of a test statistic or more extreme as a test statistic. Or in other words, what's the probability of having a value of our sample statistic? What's the probability of, okay, let me rephrase that. What is the probability of getting the sample statistic that we got or one that's more extreme? So in this case, it'll be x bar being less than or equal to, right? Match this. Less than or equal to what? Well, less than or equal to 25,000. That's what we had. So now, because we know that the distribution is normal, we're going to use this information to use in our calculator to find the probability. So we're going to use normal CDF. And the lower bound in this case is going to be what? Well, it's going to be 0, right? We could use negative 10 to the 99, but realistically, we're talking about money. And we're talking about the average, what are we talking about? The average cost of the operation. Well, you're really not going to have a cost less than free, right? So let's say 0 to the upper bound, which is 25,000. And then the mean is 26,100 under the null, so that's what we're assuming. So it's going to be 26,100. And then the standard deviation is 2,400 divided by the square root of 36. So it's going to be 2,400 divided by the square root of 36. And that's what we're going to put in our calculator. So now, that's what we're going to do. So let's put this in our calculator and see what we get for the p-value. Okay, so now, let me put it in real quick. Okay, so the mean, 26,100. Standard deviation is okay. And we want to do a left-tailed test. And our x bar is 25,000. And so if we compute the p-value turns out to be 0.003. Okay, so the p-value turns out to be 0.003. And then now we're done, because now all we have to do is compare it to alpha, right? So p-value, which is equal to 0.003, alpha, which is equal to 0.05, is p-value less than alpha? Yes. Do we reject the null? Yes. The same result, right? So now the conclusion, we go back to the claim, right? What's the claim? The claim is the alternative. If we reject the null, that means that there's evidence to support the alternative. So in this case, there is evidence to support the claim. So again, at an alpha level of 0.05, so at a significance level, so you could also phrase it this way, at a significance level of 5%, there is strong evidence to support the claim that the average cost for heart bypass surgeries is less than $26,100 based on the sample data. And that's it. Okay, so remember the phrasing, okay? So at an alpha level of 0.05, there is strong evidence to support the claim that the average cost for heart bypass surgeries is less than $26,100. Okay? So now, we're going to stop there, and next time, we're going to now talk about how do we do hypothesis testing if we don't know sigma. And that's where we're going to use the t-distribution, just like we did in Chapter 8. So one last thing before I let you go is on the critical values. So remember, there are common critical values. So just like when we talked about confidence intervals in Chapter 8, I told you that there are those common critical values for confidence intervals, those z alpha divided by 2, right? There are those common critical values like the 1.96, the 2.33, 2.576, 1.28, those, right? So for a 90% confidence interval, 99% confidence interval, 98, 95, those, okay? These are going to be the common z-scores that you're going to find for hypothesis testing. So these are in the textbook, but in fact, instead of writing them down, I just wanted to show them to you. So these are the most common critical values that you'll run into. Notice the alpha levels, 0.1, 0.05, 0.01, okay? And then notice that the critical values are different depending on whether it's a left-tailed test, a right-tailed test, or a two-tailed test. And notice that in the two-tailed test, what are you doing? You're doing alpha divided by 2, just like a confidence interval. So the two-tailed test, the two-tailed hypothesis test, the critical values are going to be exactly the same as what you would expect when we did confidence intervals. Okay? So just keep this in mind. Again, you can always get these from the calculator. And some of these you're just going to know by the sheer volume of times we're going to be going over these. So you're going to see these a lot. Okay? So other than that, I'll see you guys next time. Have a great night, and if you have any questions, just let me know. Thank you.